In this session, we discuss about link budget analysis. A link budget is an account of all power gains and losses that communication signals experience in a telecommunication system, from a transmitter to a medium like freeze cable, waveguide, fiber, etc., to the receiver. It is an equation giving the received power from the transmitting power after the attenuate of the transmitted power due to the propagation as well as the antenna gains and feed line and other losses and amplification of the signal in the receiver or any repeaters it passes through. A link budget is a design ad calculated during a design of communication system to determine the received power to ensure that information is received intelligibly and adequate signal to noise ratio. Random varying channels gains such as fading are taken into account by adding some margin dependent of anticipated severity of its effects. The amount of margin required can be reduced by the use of mitigation techniques such as antenna diversity and frequency hopping. A simple link budget equation we can be declared that received power is equal to transmitted power plus gain minus it is and losses. Note that we have to consider decibels or logarithm measurements. So adding of decibels is equivalent to multiplying the actual numeric value. For a line of sight system, the primary source of loss is decrease of a signal power due to the uniform propagation and proportional to the inverse square law. The transmitting antenna are the most part neither of isotropic nor omnidirectional. The use of omnidirectional antenna is rare in a telecommunication system. So, almost every link budget communication must consider antenna gain. Transmitting antennas typically concentrate on the signal power is a favored direction, normally that in which receiving antenna is placed. Transmitting power is efficiently increases, the systematic gain is expressed including of antenna gain, the link budget. The receiving antenna is also typically directional when properly oriented collects the more power than isotropic antenna would. As consequences, the receiving antenna gain adds received power. The antenna gains are scaled by wavelength of radiation in the cushion. This step may be required if adequate systematic link budgets are achieved. Often, link budget equations are messy and complex. So, standard practical have been evolved to simplify Ferris transmission equations into link budget equations. It includes the transmitting and receiving antenna gain and free path losses and additional losses and gains. Assume that line of sight between the transmitter and receiver. The wavelength term is a part of the free space loss part of the link budget. Once again I repeat, the wavelength term is a part of the free space loss part of the link budget. The distance between is also considerable in the free space loss. In practice situations, the transmitting and receiving antennas may be partially cross polarized. The capable between the radios and the antennas may be introduced significantly additional losses. Fresnel zone losses due to the partially obstructed line of sight path and Doppler shift induces signal power in the receiver. These are the main points in the link budget. Coming to the analysis, in evaluating of the performance, the quality of greater interest in the signal to noise ratio or EB by M0. Since a major concern is ability to detect the signal, the presence of the noise with acceptable error probability. Since in the case of satellite communication system, the most usual signal structure is modulated carrier with the constant envelope, we can use average carrier power to noise ratio, that is a C by N. as the prediction of SNR of interest. In fact, for constant envelope signaling, the predetector SNR is often expressed by the using any equivalent ratio terms, that is PR by N approximately equal to S by N approximately equal to C by N approximately equal to C by K T naught W, where K T naught W is the thermal temperature. Here PR, S, C and N are the received power, signal power, carrier power and noise power respectively, and K, T naught and W are the Boltzmann constant, temperature is under Kelvin and bandwidth respectively. My question is, here PR by N or S by N actually the same as the carrier signal to noise ratio in all times? Answer is no. The signal power and carrier power are only the same for case of constant envelope signaling. It is in the angle modulation. For example, we consider the frequency modulation. The carrier frequency expressed in terms of a modulating signal waveform m of t is S of t is equal to a cos omega t plus k integral m of t into dt, where k is a constant of the system. The average power in the modulating signal m square of t. Increasing the modulating signal power only serves to increase the frequency deviation of S of t, which means the carrier frequency is spread over a wider spectrum. But average power S square of t remains equal to a square by 2, that is a by root 2 whole square. Regarding of the power in the modulating signal, thus we can see that in FM, which is an example for the constant envelope signaling, is characterized by fact that the received power is same as the carrier power. For linear modulation, such amplification modulation, amplitude modulation, the power is carrier is quite different than the power modulating signal. For example, we consider an AM carrier with terms of a modulating signal. S of t is equal to 1 plus m of t into a cos omega t. Then S square of t is equal to 1 plus m of t whole square into a square by 2. That implies a square by 2 is multiplied by 1 plus m square of t plus 2m of t. If we assume m of t is equal to 0 means the average power can be considered as a square by 2 plus a square by 2 multiplication by m square of t. In the above equation, it should be clear that in case the power in the carrier frequency, carrier wave is not same as the signal power. In summary, the parameter of C by N and PR by N same for constant envelope signaling like PSK and for FSK, but not in non-constant envelope signaling like ASK and QAM. If you are consider envelope signaling schemes like phase shift key and frequency shift key, the value of a C by N is equal to PR by N. Otherwise, those are unequal ratio parameters. We obtain PR by N is divided by noise as followed by PR by N is approximately equal to EIRP gain by N whole divided by LS. In the above equation, apply to one or more RF link with analog receiver. The noise bandwidth seen by demodulator is usually greater than the signal bandwidth, and PR by N is the main parameter for measuring the signal detectability and the performance quality. With digital receiver, however, the correlator or matcher filter are usually implemented and signal bandwidth is taken to be equal to noise bandwidth. Rather than the consider input noise, the common formulation of a digital link is to place noise power with noise power spectral density. We can use the equation PR by N naught is approximately equal to EIRP G divided by T whole divided by K LS into L0. With the system effectiveness temperature T0 as a function of noise radiating into the antenna and the thermal noise generated by within the first stage of the receiver. Note that the receiving antenna gain G and the system temperature T0 are grouped together. The group of G by T0 is sometimes called as a receiving figure of merit, receiver figure of merit. The reason treat this explained in next session. It is important to emphasize the effective temperature T0 is the parameter of model's effect of various noise sources. The subset is treated to greater detail in after sections. We have introduced the term of L0 to represent all type of noises and the degradation factors not specifically addressed by other term of equations. The factor L0 allows for the largest absorption of different losses and noise sources catalog of earlier. In the above equation, we summarize that key parameters of a link analysis. The receiver signal power to noise ratio of spectral density, noise density, the effect of transmitting power, and the receiving figure merit and the losses LS and L0. We are developing a methodology way to keep track of the gains and losses a communication link. The net SNR arriving at the face of the detector, we are working towards a bookkeeping system much like type used in business of earmarks assets and liabilities of tails of bottom line of the profit. The above equation takes that the appearance of all of the numerical parameters are like assets of business and all denominator parameters like thermal noise, phase noise and other laws. Assuming that the receiving power PR in the modulating signal or information bearing signal, now we are related to EB by N0 and SNR from the equations. EB by N0 is approximately equal to PR by N is multiplied by W by R. If consider W is equal to 1, EB by N0 is equal to PR by N0 into 1 by R. And PR by N0 is equal to EB by N0 into R. Here R is the bit rate in some other received signal carrier power. We can still employ the above equation. Export the carrier power contributes to loss of factor L0. The fundamental relationship between the EBB0 and PR by N0 will require frequently in designing and evaluating of system performances. Now we observe EB by N0 of interest. We have referred that EB by N0 as the value of bit energy per noise spectral density required to yield a specific error property. This to facilitate calculating the margin or safety factor of M, we need to difference between the required EB by N0 and the actual received by EB by N0. From this point on, we will refer to the former as EB by N0 required and later that EB by N0 R. In the below figure, we explain that two operating points. The first is associated with PB at 10 power of minus 3. Let us call the operating point of the system required error performance. Let us assume that EB by N0 required value of 10 dB yield the required performance. Do you suppose we would build the system so that demodulator received is 10 dB value exactly? Of course, it is not. We would specify and design the system to have safety margin so that EB by N0 actually received would to be something larger than the EB by N0 required. Thus, we might design a system to operate at a second operating point in the below figure. Here, EB by N naught is equal to 12 dB with a PB is 10 power of minus 5. For example, we describe that Shapley margin link margin as a providing to order of magnitude improving of PB, or as more useful to describe the link margin providing to be more than EB by N naught. Now we are observing two operating points. One is at EB by N naught is equal to 10, that is 10 power of minus 3 PB, and EB by N naught are at 10 power of minus 5 dB. The same figure we have to consider as a reference for the above explanation. We rewrite the equations, introduce the link margin parameters M. PR by N naught is equal to EB by N naught. Then R is equal to capital M is multiplied by EB by N naught required into R. The difference decibels between the EB by N naught and EB by N naught required link margin, that is M EB by N naught under dB minus EB by N naught under required. The parameters EB by N naught required reflects the difference of one system to design another. This might be a due difference in modulation or coding scheme. A larger expected EB by N naught required may be due to the suboptimal RF system, which manifests large timing error or which allows more noise into detection process than does the ideal magic filter. Combining the equations in the above, we are getting the link margin else capital M is equal to EIRP into G divided by T naught whole divided by EB by N naught required multiplied by R K LS into L naught. In the equation of 5.23, the link margin containing of all parameters contributing the link error performance. Some of these parameters are defined with reference to practical location. For example, EB by N naught defined at an input to the receiver. More preciously, it is defined at the input to the detector, where a demodulator waveform having voltage amplitude proportional to the received energy in the basis of symbol decision. Similarly, any parameter describing received energy power, whether useful for degrading, is also defined with reference to the pre-detection point. The receiver figure of merit G by T naught is defined as the input receiving antenna, where G is the gain and receiving antenna temperature T is the effective system temperature, is also called effective system temperature. The effective radiated power EIRP is defined as the power associated with the electromagnetic wave at the output of the transmitting antenna. Each of these parameters EB by N naught and G by T naught and EIRP are defined as the reference particular system locations and now whereas. Now coming to the link budget are typically calculated by decibels. Since link budget analysis typically calculated in terms of decibels by equation M under dB is equal to EIRP plus G under dBi minus EB by N naught required under dB minus R dB bits per second minus K into T naught minus LS minus L naught, all is under dBs. Transmitting signal power EIRP expressed in decibel watts. Noise power spectral density N is under decibel watts per Hz. Antenna gain is under decibels referred for the isotropic gain, and data rate R decibels referred to the 1 bit, and all other terms are in decibels. The numeric value in the above equation parameter constitute a link budget, a useful tool for allocating communication sources. In an effort to maintain the positive margin, the mate rate of any parameter within any other parameter, we must choose reducing transmitting power by giving the excess margin, or we might elect to increase the data by reducing the EB by N naught required. Any one of the equation decibels regarding of the parameter from which it stems and just good for any other decibel, either dB or dBi. The transmission of the system. The transmission system does it not know, does it not care where the decibels has come from, as long as the need amount of EB by N naught arrives at the receiver. The desired system error performance can be met. Well, let us to add other conditions for the achieving of required error performance. First one, synchronization must be maintained and ISI distortion must be minimized or equalized. One must be asked, since the system has no preference as to where the decibels of EB by N naught come from, how shall prioritize to such an adequate numbers of decibels? The answer is, we would took for the most cost effective decibels. This goal will be steer us towards reading the next several chapters on the error corrections coding, since the discipline has to historically provided a continual reduction in the cost of electronics to achieve error performance and improvements. Now we discuss how much of link margin is enough. This question of how much of link margin should be designed into a system is asked frequently. The answer is that if all sources of gain and losses and noise have been detailed in worst case, as if the link parameters with large variance match the statistical requirements for the link availability, very little additional margin is needed. The margin needed depends on how much of confidence one has each of the link budget entries. For systems employing the new technology or new operating frequencies, one needs more margin than for the system that have been repeatedly built in and tested. Sometimes the link budget provides an allowance for the fades due to weather directly as line item. Other item, however, the required value of margin refers the link requirement for a given rain degradation. For satellite communication at C-band at 6 GHz, downlink at 4 GHz, where the parameters are well known and fairly well behaved, it should be possible to design a system with only 1 dB link margin. Receive only the television stations operating with 16 ft diameter dishes at C-band are frequently designed with only a fraction of decibel margin. However, telephone communications via satellites using standards of 99.9% availability requirement considerable more margin. Some of the Intelsat systems have 4 to 5 dB of margins. When nominal rather than worst case computations are performed, allowances are usually made unit to unit equipment variations over the operating temperature range. Line voltage variations and missions duration. Also, for free space communications, there may be an allowance of error in tracking satellite locations. Designed using higher frequencies generally call for larger margin because atmospheric losses increases with the increase of frequency and highly variable. It should be not that by product of the attenuation due to atmospheric losses is greater antenna loss. With low noise amplifier, small weather changes can reflect increase 40 to 50K antenna temperature. The shown figure link analysis proposed by Federal Communication Commission FCC by the Satellite Television Corporation for Direct Broadcasting Satellite DBS service. Notice that downlink budget is tabulated for the two alternative weather conditions. Clearly, 5 dB loss due to rain. The signal loss due to the atmospheric attenuation is only a small fraction of decibel for clear weather and is the full 5 dB during rain. The next item is the downlink tabulation. Home receiver G by D naught. The additional degradation caused by the rain, additional temperature loss radiated by the receiving antenna, making the effective system noise temperature, increases the home receiver and decreases G by D naught. Therefore, the extra margin is allowed for weather loss. Addition margin should be simultaneously added to compensate for the increase in the system noise temperature. With regard to satellite links in industry, one of often hear such expressions, a link can be closed, meaning that in decibels as positive values and required error performance will be satisfied, or link cannot be closed, meaning that margin has a negative value and the required error performance will not be satisfied, even though once the link closes or link doesn't closes, give the permission of on-off condition. In the worth emphasizing that lack of link closes of negative margin means that error performance falls short of the system requirement. Does it not necessarily mean the communications? For example, consider whose EB by N0 is 10 dB shown in the figures and EB by 8 dB. Assume that 8 dB with a PB of 10 power of 12, which is explained above figure. The margin is minus 2 dB, but the probability error is 10 times of the specified error probability. The link may be still useful through degrading. Here we explain that the EB by N0 variation of 2 units, that is 10 to 12, but change the variation of PB, that is 10 power of minus 5 to 10 power of minus 3. That is EB by N0 at 8 dB and EB by N0 at 10 dB with corresponding of PB 10 power of minus 12, the margin of minus 2 dB. That is error probability of 10 times is specified changing occurrence with respect to y-axis. Now see the table proposed direct broadcasting satellite for the satellite television clock. Shown that uplink value of earth station EARP and free space loss. Assume the rain attenuation that is variable, depends upon the atmospheric conditions, satellites and uplink. The value of a total uplink value is 102 dB Hz by considering of all the gains along with the losses. That means the link margin for the uplink is nearly 102 dB Hz. Now coming to the downlink. The downlink, we have to consider whether the particular environment is clear and the particular environment is containing of 5 dB rain attenuation. And the satellite EARP is 57. Free space loss is, suppose if you are considered clear atmospheric conditions, satellite loss 57, free space loss 206 1 dB, atmospheric attenuation, home receiver pointing loss. By considering of all these, we have to find out that the downlink approximately equal to 88.1 dB. 88.1 dB. If it is moved to the 5 dB rain attenuation, the value of a downlink is changes into 82.0 dB Hz. That means there is a variation here. There is 81.1 dB Hz. Here there is 82.0 dB Hz. We can observe that it is a condition with atmospheric is clear. This is the condition with atmospheric with 5 dB attenuation. If the atmospheric attenuation is goes on increases 5 dB to 10 dB or 10 dB to some any x value of dB, proportionally the value of a downlink is also changes. If the downlink is also changes, the effects is falls on the data which we are download from the receiver. So the link margin is changes depend upon the atmospheric conditions and free space loss and atmospheric attenuations and polarization mismatch. And we have to choose that as much of as low polarization mismatch between transmitter as well as the receiver. In some cases, we are consider the polarization mismatch is equal to 0 dB, but here we consider the polarization mismatch is approximately equal to 0.04 dB. Now we are moved to the concept of link availability. Link availability is usually to measure of long-term link utility stated on average annual basis. For a given geographical location, the link is available. Measure the percentage of time the link is to be closed. For example, a particular link between Washington DC and satellite repeater, the long-term weather pattern may be such that 10 dB weather margin is adequate link for closing 98% of the time. For 2% of the time, heavily rains results is greater than 10 dB SNR degradation, so that the link doesn't not close, since the effect of rain of SNR degradation as a function of a signal frequency link. Link availability and requirement margin must be examined the content of particular transmission frequency. Here the figure 5.10 summarize worldwide satellite link availability at a frequency of 44 GHz. The plot explains the percentage of Earth visible as a function of margin of the case of three equally-spaced geostationary satellites. A geostationary satellite is located in circular orbit in the same plane of Earth equatorial plane and synchronous altitude of 35,800 kilometers. The satellite orbit period is identically with that of the Earth rotational speed and period. Therefore, the satellite appears stationary when viewed the Earth family of visibility curve with different required links availability ranging from begin 95% availability to 99% availability. In general, the fixed link margin visibility is inversely proportional to the required availability. For the fixed availability, visibility increase monotonically with margin. Here, the figures indicating on different cases unshaded and shaded areas. The part of a Earth with 44 GHz link cannot be close to 99% of the timer of three different values link margin. Figure 5.1. The figure 5.1 explains the link coverage of such a locations of a margin value of 14 dB. Notice that figure can be used to pinpoint the regions where heaviest rainfall such as Brazil and Indonesia. The figure represents the result of link calculation per concentrate weather model of the Earth. In the figure 5.11, there will be a shaded strips on east and west boundaries of each satellite field of view. Why do you suppose the link availability is not meet these regions? At the edge of the Earth, propagation path between the satellite and ground is longer than path directly benefit the satellite. Degradation occurs in three ways. The first one, the longer path results is reduce the power density at the receiving antenna. Second one, the edge of the cover sites will experience reduces satellite antenna gain unless the satellite antenna pattern is designed to be uniform over entire field of view. Third one, propagation to the edge of Earth transversing thicker atmospheric layer. Because of this oblique path, the Earth curvature, the third item is prime important at those signal frequencies that are most attenuated by the atmosphere. Why do you suppose you do not see the same shaded areas near to the north and south poles in figure 5.11? Snowfall doesn't have same deleterious effects on the signal propagation as the rainfall. The phenomena is known as a freeze effect. In the figure 5.12, explain the parts of the Earth that can and cannot close At 44 GHz link 99% of the time with 10 dB link margin. Notice that shaded areas have grown incidentally compared with the 14 dB margin case. Now, east coast of United States and Mediterranean and most of Japan cannot close to the 99% of time. Now, in the figure 5.13, explain similar link performance for the margin of 16. Whereas 5.11 could be used to locate to region where they generate the rainfall. Figure 5.13 can be used to locate direct weather regions on the earth. Such areas are seen by southwestern parts of United States, most of Australia and coast of Peru and Chile, and the Sahara Desert in Africa. Now we observe different types of descriptions of existence fogs with respect to visibility and losses. Dense fog with a loss of 390 to 220 dB per kilometer. Thick fog 220 to 58 dB per kilometer. And up to we have to consider moderate fog, light fog, thin fog, haze, light haze, clear, very clear and extremely clear. So these are the examples are supposed to use to calculate the value of a link availability. Why? Because at the calculation of link availability, we have to consider losses along with the gains. Based on the atmospheric conditions also, the link availability will be decided. We have to discuss in the previous slides. So that's why at the calculation of a link availability for the downlink, we have to consider the loss with respect to which type of description or which type of a fog or which type of a haze that can be existence in the particular environmental condition. Link availability. When you design your UDO link, you have to ensure the availability meets the needs of applications running over air. Today's wireless networks consisting of many layers, each one having different functions. The work together a system provides a connectivity for end user. Backbone segmentations carry all user traffic to fiber termination point of data center. These wireless links are typically designed to 99.99% availability or greater or outstages on the backbone would affect all user on the system. The backbone radius of usually 0.2 point radius. The access layer of network provides the connection from the backbone to end user. The segment of network usually delivered at a point of multiple radius link availability designed 99% availability or greater. Depend upon the availability of the percentage, we have to fix the value of a downtime per year, downtime as per month and downtime as per week. If you design a system, provide internet access with a backbone, radio links are designated by 99% or greater. The access layer designed 99% or better. As a reference point in a network, design public safety network supporting policy. So, we have to consider link availability for everywhere based upon the environmental conditions and existence frequency with respect to margin. And basically, the link availability is also depends upon a few things. The first one, the most basic meaning of the link is the time the link availability divided by the time of the link is required. For fulfill period link, it would be the time link up to day individual 24 hours. If a carrier committed a guarantee of 48,000 lakhs of BPT availability, would be time the link is actually receiving 48,000 BPS divided by the time and the data rate supposed to be available. If a user guaranteed 24 hours of recognizable voice, then the link availability would be the time recognized by the voice availability divided by 24 hours. Sometimes there are disagreements about availability. For example, customer may believe it should be getting period of availability certain data rate is 10 power of 9. The provided actually is 10 power of 6. That is based upon the link availability. That means if the link availability is making success between the transmitter and receiver, there is possible to download and upload speed. But based on the atmospheric conditions, we already told that the link availability may be disturbed based upon the link margin. So that's why we have to consider all atmospheric conditions and all margin conditions and all noise considerations. Based on all this, we have to find how much of a link available on the particular time. Now let us consider what is the link analysis. What can it tell me? For the revision purpose, I take an example of satellite instant satellite for the question. The definition of satellite transmission can be summarized as the successful delivery of information from one part of the earth to another using satellite repeaters in space. A link analysis is a theoretical mathematical model of how the satellite circuit should work. It comprises of known and unknown values that must be assumed. Obviously, a link analysis is only as good as the information used in the analysis process. It is for the reason that both Intelsat engineer and Intelsat customer must have full understanding the elements involved to properly model as proposed service. To begin, one of the most familiar with elements, a satellite circuit is a complex and made up of many parts, including but not limited to a satellite transmitting antenna, a higher power amplifier, a satellite receiver, a transponder gain setting, a transponder HPA, a receiver earth station antenna, and low noise black converter. Each part must be a setup with recommended specifications and with their operating limits. To ensure the overall circuit performance is optimal for success transmission of the information. The following information is needed for the Intelsat customer to ensure to accurate link analysis. Requested satellite and transponder, downlink antenna size and the location, and uplink and HPA size and location. And also needed for the accurate link analysis for the carrier parameters, which includes data information rate, type of modulation like QPSK, 8PSK, 16 QAM, etc. And forward error correction of 1 by 2, 2 by 2, 3 by 4, 5 by 7, and etc. Outer coding schemes such as Reader-Solomon or other including DVB or DVB-S2 and etc. And finally, acceptable operating EB by N0 with thresholding value. Therefore, there is a information such as future transponder loading, adjacent satellite interference, etc., for which the exact values are not known exactly because they are dynamically and exchange over a time. The challenge is to capture the reasonable assumption of any acceptable value. One of the two paths are generally pursued. One, a more conservative approach, pursues the worst possible conditions that a link might be faced. The worst case scenario, the analysis ensures a circuit will work under the worst possible conditions. However, the cost of the customer for extra power might be economically disadvantageous. The more pragmatic path to take the provide economically sensitive and more realistic value that noted and agreed upon the advice. This is how the engineer creating a link analysis must understand need as proposed circuit. Therefore, many ways to perform the link analysis. When possible, it is preferable to begin with the factor related to the receiver station. The carrier parameters are considerable next. The determines of optimal settings to make the transponder bandwidth equal to the transponder power needed to the circuit. The work continues back to determine the optimal transmit antenna and the size of the height powered by amplifier needed to be transmitting the information to the satellite and back to the receiver station. Unless otherwise agree upon the Intelsat normal annual availability of assumption of Ku band is 99.6 for a C band is 99.96. However, important that value known and agreed upon advanced to meet customer preference. When referring to balancing services, once mean the transporter bandwidth needed to equal to transporter power need to make circuit successful. However, there are other circumstances that must have make it possible. In an instance where user transmit HPA limitation of 75 watts, one must to take carrier needs less power than bandwidth keep the transmitting earth station HPA power under 75 kilowatts. So this is an example of Intelsat satellite, how they are manage the link analysis, how they are creating the link availability between the transmitting and receiving antennas between the ground and earth station, space and earth station. So based upon all this, the Intelsat will consider the link availability and link managing between the space station and earth station. Now this we discuss topics link budget analysis and what are the how we are manage the link budget analysis based on S by N, C by N along with the temperature analysis. And after that we are creating a relation between PR by N0 and EB by N0, and we are analysis EB by N0 values based upon the PB by considering one example. And after that we are deriving link margin formula, that is M, that is equal to EIRP into G by T whole divided by S by N multiplied by R, K, LS and L0. And after that we are analysis link budget by typically calculated in decibels, with decibels and without decibels values. And after that we are how much of link margin is enough between one transmitter and one receiver. And we are taking one example of a broadcasting satellite and television crop with clear atmospheric conditions and without clear atmospheric conditions. And after that we are analysis link availability by considering of three estimating coverage, earth coverage point of view. One is earth coverage with a frequency of 44 GHz with a link margin 14 dB. Second one is with earth coverage 44 GHz with link margin of 10 dB. And third one 44 GHz with link margin of 6 dB. By all these considerations, we analysis what is the link margin. Thank you.